In order to understand the heterolytic bond formation reactions, basically reactions between nucleophiles and electrophiles, we need to understand what makes nucleophiles, and what makes electrophiles, what make electrons basically transfer from nucleophiles to electrophiles. Let's go back to that hypothetical scheme where the 2 electrons were donated by A, represented basically by a nucleophile, and that's the source that requires the electrons, so A and B, to give the hypothetical A and B molecule. Again, the 2 electrons in this case were donated by A, so A is the nucleophile, so that's the nucleophile, and B is the electron poor site, or the site that required electrons in this case, and that's described again as the electrophile. And as always, we need to keep track of electrons. So not only we need to understand why organic reactions take place, also we need to be able to keep track of electrons using Cayley arrows. And remember always, there are 2 types of organic reactions. There's radical type, which involve transfer of 1 electron or a single electron, and therefore the use of the half-headed arrow, if you like. And there's the vast majority of organic reactions which involve transfer of 2 electrons, and therefore the normal arrow, which indicates movement of 2 electrons. So in this case, we can use this arrow, again, just like before, to indicate a movement of 2 electrons from the nucleophilic A, because it has the electron density, or the electron-rich site, which goes to or transfer to B, which is the site or the species or the intermediate that requires electrons. The 2 electrons now have been used to make a covalent bond between A and B. So that's the covalent bond, and the 2 electrons of that bond came from A. So this is the electron donor, if you like. This is the electron acceptor. Let's now see or learn about different examples of nucleophiles. What's the requirement of a nucleophile? Well, it's very clear that a lone pair is a must. So a lone pair is really required. Examples, basically, if you like, neutral type. So there are neutral nucleophiles. Examples are H2O. So that is water. Now, water is a neutral nucleophile because it has the required 2 electrons necessary to make a covalent bond between, for example, water and an electrophile in general. Not only electrophile, but also not only water, but also alcohols of this general formula. And again, alcohols, just like water, are nucleophilic. They are also neutral nucleophiles because they have a lone pair. So that's alcohols. We can also add to the list amines in general. Let's also a nitrogen with 3 groups. It could be simply ammonia. It could be a primary amine, a secondary amine. Okay, the nitrogen again has a lone pair, and therefore amines are another example of a neutral nucleophile, and they behave as nucleophiles in organic reactions because they have the required lone pair. Now, nucleophiles do not have to be neutral. Some nucleophiles are actually negatively charged, which can be even more nucleophilic or better as nucleophiles. So let's learn now about negatively charged nucleophiles. And in this regard, we talk about basically the best nucleophiles that we know of in organic chemistry. Examples such as the Cn-. So this is the Cn- as an excellent, powerful nucleophile. Now Cn- is negatively charged because of the lone pair on carbon. So there's actually a lone pair here on carbon, and there's also actually a lone pair on nitrogen. If you recall, the cyanide ion has a multiple bond, which is specifically a triple bond between carbon and nitrogen, but it is carbon that's the nucleophilic center, if you like, or the nucleophilic site of the cyanide ion. So that's an example. The other example is the azide ion, which is nucleophilic at nitrogen. HS- as another example of an excellent nucleophile. And they are all negatively charged. Another example will be The thiolate ion, so that's the thiolate ion. It's also negatively charged. The hydroxide ion, for example, that's also an example of a negatively charged nucleophile. Alkoxides also, in general, alkoxides can behave as nucleophiles. So these are examples. Okay, there are probably many or others or other examples of negatively charged nucleophiles, species, if you like, or intermediates that are negatively charged. They have electron density, if you like, they are electron donors. So therefore, nucleophiles do not have to be neutral, as in water, alcohols, or amines. They can also be negatively charged, okay, just using the examples that you see in front of you. What about electrophiles? Well, electrophiles obviously should require electrons. They should be the site that needs electrons, otherwise the reaction will not take place. That's actually one reason why reaction takes place, because of the attraction based on charges. So the electrophile should have a positively charged site, and that's due to electronic effects that you know of. And we are talking about basically here about inductive effect and also resonance. So the typical electrophiles in organic chemistry are alkyl halides actually. So alkyl halides have this general structure, something like that. So this is an alkyl halide. Alkyl halides have CX bond. X is in group 7A, halogens basically. Now that carbon that's bonded to X, or the halogen, is positively charged, has a partial positive charge, and that's due to inductive effect. Inductive effect is a consequence of an unequal distribution of electrons because of the difference in electronegativity. Halogens in general are more electronegative than carbon, therefore they pull electrons toward themselves in this CX bond. So something like that denoted by this conventional arrow. Now this unequal shift of electrons due to the difference in electronegativity leaves a negative delta, if you like, or delta negative on the halogen, and a positive delta or delta positive or a partial positive charge on carbon that's bonded to them. This is called inductive effect. Inductive withdrawal with respect to carbon. Now, because of the inductive withdrawal, the withdrawal of electrons by the halogen, and therefore unequal shift of electrons in this CX bond, this carbon that's bonded to X has a partial positive charge, and because of that, that carbon is electrophilic. So that's really the electrophilic site in alkyl halides, carbons that's directly bonded to the halogen. So we can label it as electrophilic. Therefore, this carbon is electrophilic. And it is electrophilic because of inductive withdrawal, or in general because of inductive effect, which is again a consequence, if you like, or a result of the difference in electronegativity, of the higher electronegativity of halogens with respect to that of carbon. This constitutes unequal sharing of electrons in that CX bond, and therefore that CX bond, and therefore that carbon has a positive partial charge. Therefore it is electrophilic, and therefore it is also susceptible to nucleophilic attack. An attack by a nucleophile of this type, it could be neutral nucleophiles or negatively charged nucleophiles in general. But alkyl halides are not the only electrophiles in organic chemistry. We have also a very interesting, very intriguing group of or functional group, which is the carbonyl group. So this is the carbonyl group. In general, the carbonyl group is in fact present in aldehydes and ketones. The carbonyl group it's also present in carboxylic acids and in carboxylic acid derivative. The question is, why is the carbonyl group electrophilic? Well, it's clear that the carbonyl group in the carbonyl group, there is a double bond between carbon and oxygen. So there is a double bond between these two atoms, but oxygen is more electronegative than carbon. So for that, oxygen pulls electrons toward itself in this CO bond. So this can be represented by the conventional arrow or by the delta notation, so something like that. Now, this unequal shift of electrons in this carbon-oxygen double bond leaves carbon with a positive partial charge and oxygen with a negative partial charge. This is also called inductive effect or inductive withdrawal if you like to describe it. So this is inductive withdrawal also. So this makes carbon in the carbonyl group of all carbonyl compounds electrophilic. But that's not the only reason, obviously. We can also illustrate, if you like, the electrophilicity of that carbon using resonance. So we can actually break the carbon-oxygen double bond, releasing electrons to oxygen, and this would leave an isolated positive charge on carbon. If we do that, then we get something like that. And you can see the arrow. The arrow goes from the middle of that carbon-oxygen double bond, indicating breakage of a pi bond and therefore release of 2 electrons to oxygen, which already has 2 lone pairs. So there were 2 lone pairs before. If we do this, we can get, if you like, another resonance structure. For this general carbonyl compound, it's clear in the resonance structure that carbon has now a positive charge and oxygen has a negative charge. Now that's a result of the breakage of that carbon-oxygen double bond, if you like, resonance. So this is like resonance withdrawal. Therefore, this carbon in the carbonyl groups is also electrophilic. And if it is electrophilic due to resonance and inductive withdrawal in this case, that carbon is susceptible to nucleophilic attack. We will see the chemistry of carbonyl compounds in due course. For now, this is only to illustrate the idea that carbonyl groups are typical electrophiles in organic chemistry. Within carbonyl groups, there are different function groups. You are talking basically about aldehydes and ketones on one hand, and aldehydes and ketones undergo nucleophilic addition type reactions. There are also carboxylic acids and carboxylic acid derivatives. And carboxylic acid derivatives, they have their own class, if you like, or their own type of organic reactions. Not only nucleophilic addition, but actually nucleophilic acyl substitution. That's because carboxylic acid derivatives contain a leaving group. So typical electrophiles, in summary, in organic chemistry are alkyl halides, carbonyl compounds. We can think also of carbocations. Okay, carbocations are formed when alkyl halides dissociate, if you like, when the CX bond in alkyl halides breaks up, leaving a positive charge on carbon, and therefore leaving an isolated positive charge on carbon that's bonded to X in the alkyl halide. We are talking basically about a carbocation of this type, so something like Cr3, and there is a positive charge on carbon. This is the carbon electrophile, a carbocation. So this is called a carbocation as an example of electrophiles in organic chemistry. So we can have carbocations, we can have partial positively charged carbon as a result of electronic effects, such as inductive effect in the case of alkyl halides, inductive effect and resonance in the case of carbonyl compounds. The proton itself, by the way, is also a typical electrophile. So we can also write it down. So that's the proton, H plus, as a typical electrophile also in chemistry. So to sum this up, to wrap this up, organic reactions involve reactions between nucleophiles and electrophiles. Nucleophiles are the source of electrons, the electron dense source, if you like, the electron donor, if you like. Now these electrons from the nucleophile are then donated or used to make a covalent bond between the nucleophile and an electron poor site, or a site that requires electron acceptor, if you like, or the electrophile. So it's reactions between a nucleophile and an electrophile. Nucleophiles can either be neutral, as in the case of water, alcohols, and amines. They can either be negatively charged, as in the cyanide ion, for example, or alkoxides. Electrophiles can be positively charged carbons, so they can be isolated or partial, isolated as in the case of carbocations, partial as a result of electronic effects such as inductive effect and resonance, exemplified by alkyl halides and carbonyl compounds.